My name is Yogesh Gianchandi, and as Dale said, I am with the EECS department at the University of Michigan, and I'm just wrapping up a program manager appointment with the NSF. Some of the sensors that you're going to that you've heard about of that nature, and some of the other ones that I'm going to talk about are in fact funded by my program. I had a few slides on the background of the organization, but I'm going to, is there a pointer here? Rather stand. Thanks. But I'm going to go through these really quickly. You know, this is an agency with a very broad mandate and a constrained budget. There are seven different directorates. I belong in the Directorate of Engineering, but there are many other directorates here that are relevant for the kinds of things that are being discussed here: geosciences, biological sciences, and so on. And within the engineering division, we have within the engineering directorate, we have 5 different divisions. 3 are topical: chemical, biological, and environmental, civil, mechanical, and well, that's a typo, and it's industrial, and ECCS, where I belong here. And then we have industrial innovation and EEC, which funds centers. This funds SBIRs. There isn't any division that I know that is not interested in this type of work. So there are funding opportunities across the board. These are some of the examples of NSF investment areas in recent years. So you see the climate change science program. The budget request is $220 million for this fiscal year. I think cyber infrastructure also relates to this. Water, dynamics of water processes in the environment is also relevant to this. My own research interests and those of my program are focused on microsystems, and these have applications in a lot of different areas. But environmental monitoring is certainly one of the primary drivers. Biomedical is another one of the important drivers. But you can see there's other things over here that would also relate to HEMBI: transportation systems and smart homes, and perhaps even some of the stuff that's environmental but perhaps extraterrestrial. You've already seen many examples in the previous talk of the kinds of sensors that are used for pressure, temperature, humidity, and vibration. There's a lot of activity in hybrid modules and also increasing activity in monolithic modules. This is a slide from about 5-6 years ago from Ken Wise's research at Michigan. Here's just an example of the level of integration that was achieved. This is a 0.2 cc without a battery. The vision is to be able to just put something like this on a battery cell, or integrate the cell into the assembly itself. It's got a microcontroller, a very low power, stack of sensors: pressure, temperature, humidity, accelerometer. And actually this one also had off-board neural electrodes, because there's a lot of interest in neural prostheses over at the program there. There was some innovation in how the whole thing was integrated with micro connections as well. Power, and it was memory, and then it was running off a 3-volt lithium cell. One of the talks coming up, Dr. John Burt is going to talk about work from University of Washington. This is partly funded out of my program now. with a grant to Brian Otis, and they are building wireless nodes to mount on birds, I believe, and I'm going to let him talk more about it, but you can see where the technology is now. This is their current generation. I pictured on a quarter here is a really small hybrid module, just using off-the-shelf electronics with memory, transceiver, and it has power on the order of a few milliwatts or maybe a few tens of milliwatts. That may be on the high end of what can be powered by energy harvesting, but their next generation, which looks like it's well on its way, this is 2 millimeters on the side. That's going to be an order of magnitude or 2 orders of magnitude lower power, and that would be suitable for energy harvesting. This is Mike Flynn's work with Fatih Kocher, which was published in the Journal of Solid State Circuits a few years ago, where they tried to make RFID. They tried to make RFID technology and then combined it with sensing. And here they had a temperature sensor that was built on board this, and it was wirelessly communicating. That's a 1 millimeter chip with a 900 megahertz communication band, built in quarter micron CMOS. Same group published more recently work where they had a higher communication band, 2.4 gigahertz here, but they had a record energy efficiency here, 5.8 nanojoules per bit. This is actually the first super regenerative radio. It's an old concept, but has not been reduced to practice in IC form until quite recently, until this work actually. And it's quite promising for the kinds of sensors that are being developed right now. Jerry Lynch is working on, he's in the civil engineering department, and he is interested in monitoring bridges and buildings and measuring vibration in them. So he developed this work, which is a hybrid module. As you can see, it's a little bit larger, but it's got actuation and sensing channels, and again, a 2.4 gigahertz transceiver, data converters, and so on. Obviously, battery powered. This is well beyond what you can do with scavenged power. He is actually testing these on the FSF-1 Sea Fighter, which is a high-speed aluminum ship, and to monitor its vibration as it makes its way from Florida to Oregon. So that's the first category. There's a lot of work that's also been done in gas phase chemical sensing, both in hybrid modules and now increasingly in monolithic implementations. So this is also work from Wise and Zellers. This is funded out of NSF, Engineering Research Center's grant. And the way these sensors are intended to work is that the incoming sample is filtered and then goes into a pre-concentrator where you can sample, where you can accumulate the sample of interest over time, and then desorb it. When you're ready to do the test, it goes through a separation column and then another separation column with some temperature programming, and that separates out the mixture, which is then passed over the sensor array. So this is really the way to go for gas mixtures, because the detectors themselves don't offer the discrimination that's necessary to break apart these complex mixtures. Here you see various generations of hybrid assemblies here. This is actually a gas separation column. Now, typically these are large, on the order of tens of centimeters. Here you can see this is, I think, a 1 or a 3 meter column that has been miniaturized. And on the next slide, I have, well, this is also a separation column against a dime. And you can get some record performances. I'm not a chromatographer myself, so I can't really comment too much in detail on this. But they have achieved some world records in the ability to separate. Because as you shrink down here, the separation occurs faster than it would normally. So things that might take 10, 15 minutes normally will take probably a few minutes or less now. Here are actually the pre-concentrators, again in single chip form, where the gas flows through. Some species are absorbed onto the sidewalls of whatever is embedded in here, and then when you heat it, it comes back out and you flow it through your separation column. That allows you to get down to a part per billion or sub-part per billion resolution. Right now, the same team is developing a 3-chip module where they will have a pre-concentrator, separation column, and then a detector. And these chips will all just plug into each other. One of the things to keep in mind is that to the extent that temperature programming is used here, it provides much higher speed, when you scale down than you can get when you have larger devices. Liquid phase chemical sensing. There was a company recently acquired by General Electric called Sensicor that developed this technology. It might get farmed out again, is what I hear. This is a handheld water sensor, and it can do a number of colorimetric tests for fluoride, iron, copper, and other common contaminants. And that's the production version. Obviously, the research versions are further along. This was the initial device, I think. pH, chlorine, conductivity, ammonia, so on and so forth, calcium. Quite a lot of data. Some other research that has been going on for even smaller devices is spectroscopic. So here is a discharge, micro-discharge based device for emission spectroscopy. The way inorganic contaminants in water are often measured is by the emission signatures. So here you can have a monolithic device where discharge is fired between an electrode and a liquid sample, and that could be part of a microfluidic chip. And then you do emission spectroscopy on this, and you can pick up different species even without pre-concentration. So this is a few ppm. It gets down to maybe on the order of 1 ppm without pre-concentration. That's one of the problems with these micro devices. As you get smaller and smaller, your ability to sample large environments reduces, and you really have to use some sort of a pre-concentration. Here is the same device connected to a PDA here with a portable USB interfaced spectrometer, and actually a chip that can be swapped. This same discharge can also be used for vapor phase sampling, but it's less sensitive without a pre-concentrator again. So this chip has a porous region which serves as a reservoir, and then fires a discharge in the air between this anode and the cathode that forces the species in the reservoir to be ionized, and then you do emission spectroscopy through the optical fiber connected here. Finally, radiation detectors are also being developed, and There is, and there's been work over the last couple of decades, I would say, in miniaturizing radiation sensors. There's solid-state radiation sensors, and of course, there's the gas discharge-based sensors, which are basically miniature Geiger counters. They've been used for X-rays and other things, and so on. But there is a scope for taking the technology a bit further, because the micro-discharge, the way the Geiger counter works is you have a cavity which is gas-filled, and there's a high electric field there. A beta particle enters, causes a breakdown, and that electrical breakdown that occurs registers as a click. So you have an event. But you can, if you tailor the gas mix in there correctly and you just do the right kind of engineering there, you can use that discharge as a wireless transmission itself. Okay, like a Marconi transmitter. So if you do it right, you can get up to about 3 gigahertz of signal there. So it's extremely low power. We are talking about microjoules of energy, and it provides both the sensing and the transmission function. These are recent results where actually even gamma rays have been detected in this way. I'm not going to go over the details. You can contact me later if you're interested. But you can see this is a 1.2 gigahertz signal coming with gamma ray. The only thing with gamma rays is you need to have a metal conversion layer that will convert the gamma to an electron, to a beta particle. But that's the way it's done conventionally as well. So in conclusion, there are many opportunities for engineering research in micro devices. Of course, there's a continuing need for research in sensors that are selective and power efficient. And those are, I think, the two of the biggest challenges in designing the sensors. A lot of the sensors sense far more than they should. Robust packaging is obviously important, particularly in some of the emerging applications. So for example, there are projects where sensors are being used for underwater and underground exploration, and those are extreme environments, and that's going to challenge the current packaging technologies. Low power circuits, there's a lot of activity in that already, particularly for communication systems, and that's good. Portable power is going to continue to be a problem, because for a lot of the things, a lot of the applications that are interesting, the existing solutions for power scavenging are not going to work out. It's important to identify practical challenges and work in interdisciplinary teams, and I see from the attendance list at this workshop that this is going to go toward that. So thank you very much.